So let's do a couple problems using the CLT for means. So we said that in the previous video that if as long as n is greater than or equal to 30, this x bar, this sample mean will be normally distributed with a mean of mu and a standard error or standard deviation of sigma over square root of n. Now there was a couple of conditions, so I kind of wrote this in blue. So if the population distribution in the beginning is normal, then the sample size doesn't really matter. Sample size does not matter. You always will get a normal curve for x bar. If the population distribution is not normal, so if it's skewed or uniform or something else, then x bar will have to be normal only if n is greater than or equal to 30. If it's not normal, okay, and if the original population is not normal and n is less than 30, then x bar is definitely not normal either. Okay, so let's first start working with some of these assumptions. So here's an example. So using the assumptions for the CLT for means, determine if x bar will follow a normal distribution. So the first part says the initial population is normal and we obtain 37 samples. Okay, so what do we know? So we know that the initial population is normal. Oh, so that's done, because if we know that it's normal, that's case number one. If it's normal, the sample size doesn't even matter. It doesn't matter how big I make the sample. My x bar is still going to be normal distribution. Okay, so even though it's normal, and it's still greater than 30, it doesn't matter though. The fact that it's normal overweights it. So x bar will still be normal. And this is basically case one. Okay, so it satisfies this first case. Okay, so now let's look at part B. So the initial population is normal and we obtain 19 samples. Well, we already know that it's normal, so actually n doesn't even matter. It doesn't matter if 19 samples, okay, well 19 samples is less than 30, okay? That doesn't matter. The fact that it's normal overweights it. So x bar will still be normal. Okay, this is also case number one again. Okay, case number one. All right, so part C, initial population is skewed left and we obtain 21 samples. Okay, so it's no longer normal. So now we know that this thing is skewed left. Okay, and so now when something is not normal, that's going to be case number two. Case number two says when the population is not normal, then what we're going to be looking at, we have to look at the value of n. Is n greater than or equal to 30? Well, in this case, we have 21 samples. 21 is not greater than or equal to 30. So what we're going to say is x bar is not normal. Because n is less than 30 and initial population is not normal. Okay? So none of it got satisfied. The fact that it was a normal and the fact that it wasn't greater than 30. So this is basically case number 3, not normal and n is less than 30. So this is just case 3. Okay, and then part D just basically says initial population is uniform. Okay, so it's uniform and then we obtain 100 samples. Okay, so because it was uniform, okay, so we know it's uniform, that's not normal. Okay, so basically we're in case 2 again. It's not normal. So now we got to check if n is greater than or equal to 30. In this case, 100 is greater than 30. So x bar will be normal. X bar is normal because n is greater than or equal to 30, which in this case is 100. 100 is greater than or equal to 30. So even though the initial population was not normal, the n value was able to be large enough. Okay, so this is basically case number 2. Okay, so make sure that you really know how to do some problems like this, because this will be on the exam. I will have some problems where you have to determine if something if x bar will be normal or not. Okay, so now let's do a concrete example. Okay, so now let's do this example. So suppose that the GPA of STEM majors is skewed left with a mean of 3.7 and a standard deviation of 0.3. Okay, so this sounds like a very basic normal distribution problem. The only thing is that this time it's not normal. We see that it's skewed left. Okay. So we have a mean of the initial population of the GPA, and we also have a standard deviation. Okay. So my question here is, can the CLT for means be used with 28 samples? What about 35 samples? So we got to check, can we use it for 28 and can we use it for 35? So one thing to note is that we have skewed left. This is not normal, okay? Which means that we have to look at the value of n. N has to be greater than or equal to 30. Here we start off with 28. Is 28 greater than or equal to 30? No, it's not. So for this one, cannot be used. So I cannot use the central limit theorem, or x bar is not normal with n is equal to 28. When it's n equals 35, well, 35 clearly is greater than or equal to 30, so it can be used when it's equal to 35. So even though we didn't get normal, it was skewed left, doesn't matter, our n satisfied. Okay. So now let's go to part B. Part B says fill out the sampling distribution for the sample mean if we obtain 35 STEM students. So remember that x bar, if we look at the central limit theorem, we go all the way back up. The central limit theorem for the sample mean was that the mean is mu and the standard deviation is sigma over square root of n. Okay, so the way that I like writing it is that the mean of x bar is going to be just mu, and the standard deviation of x bar is going to be sigma over square root of n. Okay, so it's kind of like how we wrote it with proportions, okay, with sample proportions. The mean in this case is going to be what? Well, what's the mean? The mean in this case is just going to be 3.7. So this guy is just going to be 3.7. The standard deviation of the sample mean, sigma, if we look at sigma, sigma was 0.3. Divided by square root of n. And in this case, it's going to be 35 because we're getting 35 students. So let's put this in our calculator. So we're going to do 0.3 divided by the square root of 35. And if I round that to 2 decimal places, I'm going to get 0.05. So that means that the mean here is going to be 3.5. And the standard deviation is going to be 0.05. Okay, so that's my sampling distribution. You're just plugging in the numbers, okay, of this. Okay. All right, now that we have our mean, remember this is our mean, and you can think about this. This is my sigma, the one that we're going to look at the calculator. This is my standard deviation or my standard error, another fancy word. Okay, so now let's do part C. Find the probability that the mean GPA of the 35 students will be less than 3.4. So for example, what this is saying is that if I get these 35 students, I get all of their GPAs, what is the probability that their mean GPA combined together will be less than 3.4? Okay, so let's draw a normal curve. The mean of the mean GPA will be, according to this, 3.5. So this is just going to be 3.5. We want the mean GPA to be less than 3.4. So here is 3.4, and we want it to be less than that. So remember, here is negative infinity. So what we're going to do, we're going to use normal CDF. So it's going to be norm CDF. My lower bound is going to be equal to negative infinity. My upper bound is going to be equal to 3.4. My mean is equal to 3.5. And my standard deviation, or my sigma, well, that's the only thing that really changed. My sigma is going to be this 0.05 that I have up here. So 0.05. Okay, so I'm going to put this in my calculator. Second data, distributions, normal CDF. The mean is going to be 3.5. My sigma is going to be 0.05. My lower bound is negative infinity. My upper bound is going to be 3.4. So when I calculate that, I'm going to get 0.0228 around there. So that's the probability that the mean GPA of these 35 students that I captured, okay, will be less than 3.4. Okay. Now let's do the last problem. So find the sample mean of the 35 students, that is the 90th percentile. So notice here, the key word is percentile. When we look at percentile, what we're looking for is inverse norm. So basically, if you want to look at it in a picture, the mean, remember, is 3.5. We're looking for what sample mean will give me 90% below it, because it's 90%, so 0.9. So we're going to use inverse normal. The area to the left is just 0.9. My mean still hasn't changed, it's still 3.5. My standard deviation, if we go back up, is going to be 0.05. Okay, so that one's just still based on this guy. So 0.05. So I'm going to go ahead and put this into my calculator. Second data, distributions, inverse normal. So it's not going to be 0.9. Means is 3.5. Standard deviation is 0.05. So my answer is going to be a mean GPA of 3.56 is going to be the 90th percentile. Okay? So these problems are just like the central limit theorem for proportions. It's just a different formula. But we're still calculating the same problems. We're still using normal CDF. We're still using inverse normal. We're still calculating the sampling distribution, and we're testing conditions. So just the same thing as proportions. It's just that now we have different conditions. Okay?